Okay, before I move into this video, I'd like to give you a little bit of nomenclature here. So if we have a function f of x, this can be rewritten as a y. These are equivalent. And so there's two ways of expressing a derivative. If we want to say something's a derivative of f of x, we simply say f prime of x. That's a really quick way to get to the derivative. But this is the Newtonian way of expressing it, but if we want to go with the Leibniz notation, we say that we go on the right side and we call it dy dx. And this means that we're getting a small change in y over a small change in x. And that's what they're saying. That's what this means. But all that you really have to know is that if we're saying dy dx, we're talking about the derivative of y, and f prime of x is the derivative of f of x, but these are really the same exact thing. So now that we've gotten that over with, let's go into the definition I found in my textbook for the derivative of a constant function. And that says df dx. So actually the derivative of f of x, df dx, equals d by dx equals the derivative of, if equals the derivative of c, a constant function, that derivative is going to be 0. Now what this means is if you have a constant c, a constant being any number basically that doesn't change as x changes. So if we say that if we have a graph where if we have a graph and we move along the x-axis and the value never changes, so that would be if we have a constant function like this, where this is 5, or something up here like this is 10. What this means is the derivative for each of these functions here is 0, and that should be it should be really obvious why that is. And that's just because the slope at every point on here is going to be 0, no matter where you go. I mean, it's just really obvious why that is. But the reason that your textbook and my textbook would point this out is because we can use this as a shortcut later. But for now, we'll just check it off, and we'll just keep this in mind. Now, I'll clean this up because the power rule here is going to be really, really important. It is essential that you understand this because it makes things so much faster, and it's really, if you don't know how to use the power rule, it's just super important because it saves so much time. So let's get into it. We saw that the derivative of x squared from the other videos, I'm going to use this notation, the derivative of, or actually let me get rid of this, the derivative of x squared equals 2x, and the derivative of x cubed equals 3x squared. Now, what we see here is that there is kind of a pattern here. It's not easy to tell just from looking at these two, but I wanted to just show you these in advance so we can look at these in a second. Now, the power rule is simply a definition. It says d by dx of x to the n equals n, there's going to be n times x to the n minus 1. Now, I don't know if you're following this yet, But what this says is, if you have something x to a certain power, to find the derivative of this, all you do is bring this n down in front of the function and decrease n by 1. Now you'll notice that's exactly what happened here. We brought the 2 down in front of here, so we have 2x, and then we decrease this 2 by 1, so all this is x to the 1, and that doesn't show up. But that's exactly what we're seeing here. Now, the same thing goes over here. We take the 3 down in front of it, and then decrease the power by 1. So this 3 shows up in front, and now we have x squared here. And I'm pretty sure that you can prove this if you just do this derivative. And let's see. Now, I'm pretty sure to prove this, to actually do this derivative, you need to use the binomial theorem, and it's a lot of work, but it's definitely a good idea to look up this definition so that you know what you're dealing with. But for now, you can just use it as a shortcut. So that's our power rule. And since I've only got 6.5 minutes on this video so far, I'm going to do a little bonus. The next thing we can look at is the constant multiple rule, I think it's called. I was planning to do this in another video, but since I got through this pretty quickly, I'll show you how you can use this in combination with the power rule. The constant multiplication rule says that if you have something like, so for x squared, we bring this 2 down. What we can do is take the 2, sorry, get ahead of myself. If we take this instead of x squared, 2x squared, and find the derivative of this, what we can do is take the 2 out. If we're multiplying by a constant like 2, we can take it out. So what we have is, this is equivalent to the 2 times the derivative of x squared. So we're not even going to bother interacting with this 2. We just pull it out of there, do the derivative of the inside, and then multiply it again. So what we have is 2 times this derivative, which is 2x, and overall this equals 4x. So now I may have gone a little too quickly on this, so let's look at some more of these. If I want to do the derivative of x to the 7th, or not equals d by dx of x to the 7th, this equals, pull the 7 down, see this is our n, so n shows up in front, if 7 is n, times x, times, or to the n minus 1, which is 6. It's that simple. That's our derivative. Now, we can combine it with this constant multiple rule and say if we had d by dx of, let's say for example 2x to the 7th, the derivative of 2x to the 7th equals 2 times the derivative, we can just pull this 2 out, 2 times the derivative of just x to the 7th. And we have that already here, so we can just do this, 2 times 7x to the 6th, and this equals 14x to the 6th. Okay, hopefully that makes sense. Let me know if I have to come back and do an extra video on this, because this is really important. And there's a lot of stuff here, so make sure you completely understand it and get what's going on with all this, because we start to get into some pretty heavy things with the chain rule and some other crazy names that you'll end up learning when you do derivatives, but I hope this makes sense, and I'll see you in the next video.